Hello again. So now we're looking at section 1.8 of Rosen's text, Proof Methods and Strategies. Now, if I was to summarize this section, I would just say there's basically 3 or 4 different proof methods or strategy or types of proof that we're going to look at. So these general strategies for proofs are encapsulated by the names for the approach one takes for these types. A proof by exhaustion, or also called an exhaustive proof, basically handles one by one all the various cases that you would need to show to be true for a particular quantity. So this might involve X being positive or negative or 0. So those would be the cases that you'd have to prove whatever the proposition is holds true for each of those cases. An existence proof simply involves showing a particular quantity exists. Okay, so prove that there's 3 integers so that a squared plus b squared equals c squared, so that they work in that formula. Well, that would be pretty easy to, especially because that's a Pythagorean theorem, and you know that there's 3 integers that work with that, like 3, 4, and 5. The third type is called a uniqueness proof, and this involves not showing a quantity exists, but showing that it is unique, some quantity is unique, that another such quantity does not exist. And so we'll talk about that. Now, in an exhaustive proof, you have to show that a proposition holds true for all the possible cases that could be. All right? So that if you wanted to prove that if n is an integer, that n squared would be greater than or equal to n. Okay? If n is an integer, n squared is greater than or equal to n. Now that is not necessarily true if n is not an integer. Like in the case of 0.5. If n was 0.5, what's 0.5 squared? Well, that's 0.25. And 0.25 is not greater than or equal to 0.5. But if n is an integer, this will be true. Now, there are 3 possible cases, and the proof talks about them. Consider 3 possible cases when n is 0, when n is negative, and when n is positive. All right? So, A, if n is 0, then 0 squared is equal to 0, so therefore 0 squared is greater than or equal to 0. So n squared is greater than or equal to n in that case. If n is less than 0, and yet n is an integer, so the highest negative integer is -1. So n would be less than or equal to -1. Now, n squared, when you have a negative number, is greater than 0, which would be greater than n if n was -1. 0 is greater than any negative number. So therefore, n squared would be greater than n in that case. So that holds true. Of course, when you're squaring a negative, you get a positive. And any positive number is greater than 0. And therefore greater than -1. In case C, if n is greater than 0 and n is an integer, then n it would be greater than or equal to 1 because the lowest positive integer is 1. If you multiply both sides of that inequality, n is greater than 1, greater than or equal to 1, by n, you get n squared greater than or equal to n. And just taking this equation, n is greater than or equal to 1, multiplying both sides by n, you get what we're trying to prove, that n squared is greater than or equal to n. So because n squared is greater than or equal to n holds true in all possible cases, because n is either 0 or positive or negative. Those are the only possibilities. Then if n is an integer, then n squared would be greater than or equal to n. Okay, more on proofs of exhaustion. You might look at page 94, example 4 of the Rosen text. They prove the proposition that absolute value of x times y is equal to absolute value of x times absolute value y. And it's proven for all cases of x or y being either positive or negative. So there's a lot of cases here when you have two variables and they can either be positive or negative. They could be both positive, so you handle that case. It could be that x is positive and y is negative. That's another case. Or it could be x is negative and y is positive. Or it could be both of them are negative. So you have several cases, 4 cases, and you can look at this equation and note that x and y could be switched in their positions in that equation. Instead of xy equals absolute value of x, absolute value of y, that could be switched around and be yx equals absolute value of y times absolute value of x. So in other words, x and y could switch or exchange places and it would still be true. So we could say the case where x is positive and y is negative, or x is negative and y is positive, could be treated as one case, and because we could like switch where the position of the positive and the negative around, it won't be any different. So we say we could treat it as one case without loss of generality. We use that phrase, without loss of generality, which means that it doesn't affect how general we could the application of this proof would be. So another good example about of the without loss of generality aspect is Rosen's example 7 on page 95. Now let's look at a proof where there's an error, and the error comes when we don't try all the possible cases that exist. We're missing a case. See if you can tell what case is missing. So the theorem that we're trying, or the conjecture that we're trying to prove is, if x is a real number, then x squared is positive. Proof: if x is positive, then the product x times y, or x squared, would be positive. If x is negative, then the product x times x, or x squared, is again positive, since it's the product of two negative numbers. Thus, when x is a real number, x squared is positive. So there's a hole missing in this proof. Can anyone tell what it is? Well, if you've guessed that we didn't handle the case where x is 0, that's correct. We are missing the case of x being 0. You must try all the possibilities for your variable. And so if x was 0, then we'd have 0 times 0, which is 0. So it's not true that whenever x is a real number, then x squared is positive. Because if x was 0, then it's 0, not positive. Now, if you change the theorem or the conjecture to if x is a non-zero real number, then that would be true that x squared is positive. Now, existence proofs, basically all you have to do is show that there's at least one example of a particular situation. So look at this first proof. Prove that there exists a prime number p such that p plus 2 and p plus 6 are also prime numbers. So here we must simply find a prime number fitting these criteria. The prime numbers begin with 2, 3, 5, 7, 11, and 13. So we can start with these. After a minute, you soon realize that 5 fits the criteria. Why is that? Well, when p is 5, that's a prime number, right? Is 5 plus 2 a prime number? Yes. 5 plus 2 is 7, and that's a prime number. And is 5 plus 6 a prime number? Yes. 11 is a prime number. So we have just proven that there exists a prime number p such that p plus 2 and p plus 6 are also prime numbers. Okay? Then, looking at the bottom example, prove that there is an odd integer that can be written as the sum of two squares. An odd integer that can be written as the sum of two squares. Now, essentially, we need to find two integers a and b so that a squared plus b squared would equal c for some odd integer c. So if it's helpful to write it in algebraic notation for you to understand exactly what we're looking for, then go ahead and do so. Now, since an integer is the same parity, even odd, as its square, and an odd results from adding an even and an odd, then you need to pick a and b to be different parities. See, we know that if I picked a to be an even number and I square it, that's going to be even. And if I pick b to be an odd number and I square it, that's going to be odd. And then when you add an even and an odd, you get an odd. And that's what we need to do. So let's see. Just pick a and b to be different parity. So one even, one odd. So I picked 2 and 3. So a squared plus b squared would be 2 squared plus 3 squared, which is 4 plus 9, or 13, which is an odd integer. So there exists an odd integer that can be written as the sum of two squares. All right. Now, uniqueness proofs are the third type. And to show that a quantity is unique, we have to basically show that assuming that there's another one is impossible. Okay, so let's look at that. Show that if a and b are real numbers and a is not 0, then there is a unique real number r such that ar plus b equals 0. Okay, so we have to show that there's a unique real number r. So r is what we're going to pretend. We're going to sort of pretend that there's another r. So let's look at the proof. First, we see that the real number r would be negative b over a. So you basically solve this equation for r. And you move the b to the other side and then divide by a, so you get negative b over a. That's a solution of the equation ar plus b equals 0. And I just basically plugged negative b over a back into the equation, and we showed that it equals 0. Consequently, a real number r exists for which ar plus b equals 0. So we've proved the existence part of it, okay? But we didn't yet prove the uniqueness part, all right? So here's how you prove the uniqueness. Suppose that s is a real number such that as plus b equals 0. So we're calling it something different, and we're sort of supposing that there's another one, all right? Another value, s this time, such that as plus b equals 0. Now, ar plus b is 0, and if our assumption that there's another one is also 0, AS plus B equals 0 also, then I can set AR plus B equal to 0, which is equal to AS plus B, and then you can basically solve this equation. So subtract B from both sides, and so we get we're subtracting B from this side, so it'll be just AR. We're subtracting B from AS plus B, so it'll be just be AS. And then we divide both sides of the equation by A, and we get R equals S. Okay, so in the second part of the proof, we had supposed that if AS plus B equals 0, so if there's another one where AS plus B equals 0, then that would mean that R equals S. But what is the contrapositive of that? Well, the contrapositive of that is if it's not true that R equals S, so in other words, if S is not equal to R, if the two are not equal, then AS plus B is not equal to 0. So that means that it's not another one. So we basically have proven that there is not another unique real number so that AR plus B equals 0. Okay. This game is similar to what's required for a proof, describing a winning strategy for this game. So here's this game. Suppose two people play a game taking turns removing 1, 2, or 3 stones at a time from a pile that begins with 15 stones. So on that person's turn, he or she must take at least 1 stone and not more than 3 stones. Excuse me. The person who removes the last stone wins the game. Okay? Now, that last stone, by the last stone, I mean whoever clears off the board. He doesn't just take 1 stone. He takes either 1, 2, or 3 stones in his last move. Every move, someone does 1, 2, or 3 stones. So prove that the first player can win the game no matter what the second player does. Okay? So here's the proof. Okay. If we start off with 15, if the first player chooses 3 stones, then that'll leave 12 stones. Okay? Now 12 is a multiple of 4, and that's the magic key to this. No matter what the next person does, as long as you pick stones to leave multiple of 4 again, it forces you to win. All right, so let me explain that. So the first person, like I said, he's the guy trying to win. He picks 3, so now there's 12 stones. So let's say if the next guy chooses 1 stone, okay, so now there's 11. Well, just pick 3 stones again, so that'll make 8, which is a multiple of 4. So you're always trying to make a multiple 4 left over. Now, if the person going second had chosen 2 stones, then that means that there would be 10 stones. Then you'd only take 2 stones. The player trying to win would only take 2 stones next, leaving 8 again. So you can always go down to 8 stones from 12 stones after your opponent picks either 1, 2, or 3. Then you just pick whatever the difference is to make it down to a multiple of 4 again. So now we're down to a multiple of 8. Now you just repeat that and go down to a multiple of 4, and then your opponent will pick either 1, 2, or 3 stones, but he can't pick all 4 of them. So let's say he picks 1 stone. Well, that leaves 3 to go, and you just get those 3, and so you've chosen the last stone. Or if your opponent picks 2, then you pick the remaining 2 and you pick the last stone. Or if the opponent picks 3, that still leaves 1 stone that you get the remaining stone. So that's how to win this game. So it's just this repetitive process, and it shows that you can always win the game. Now, in the Rosen text, it talks about a game, something about chomping game, where cookies, and the idea is to not choose the last poisoned cookie. There's one poisoned cookie, the last one, and it discusses that in terms of um, a winning strategy. Now, proofs are a multifaceted skill. It's called a heuristic skill, and you can just play around with it. You don't have to think, oh, I'm not getting it and I'm frustrated. Well, just play around with them and try to make headway, testing and just trying to discover a method. Sometimes you'll work forward, sometimes you'll work backwards from what you're trying to prove and try to figure out, well, what do I need to know in order to get there? Or sometimes you'll move from the middle. You think something's true and you can go from both ways, and then eventually you'll figure out how to go from the beginning to the end. So just try your hand at it. Let me know if you have any questions.